Hey guys, Spider Man back talking to you about basic differentiation rules. Another question, what did Iron Man say to Ant-Man and the Wasp? Stop bugging me! Yeah, the first thing we're going to talk about is the constant rule. That says the derivative of a constant function is 0. That is, if c is a real number, then d dx of c, the derivative of c, some number, is equal to 0. So remember, a constant function is just like y equals 5 or f of x equals negative 1/2. It's just when you have a function, y or f of x, equal a number. So let's show you how this works. If you take the derivative of a number, it's always equal to 0. Here's why. We start with f of x is equal to 5. That is our constant function. So if we want to take the derivative of f, what we do is we use the limit process, and this is the formal definition of the derivative. So we take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So here it says f of x plus delta x. That means you're going to plug in x plus delta x for x in our particular function. But our function just has a 5 in it. There's no x. So what we're going to do is just plug in 5. Since there's no x's, you can't plug in x plus delta x. You just keep this 5. F of x over here is also 5. So you get the limit as delta x approaches 0 of 5 minus 5 over delta x, which is just the limit as delta x approaches 0 of 0 over some number. And 0 over some number is going to be equal to 0. Now we take the limit as delta x approaches 0 and you get 0. Anytime you take the limit of a number, it's just equal to that number. So here we've shown that if you were to take a constant function, this could have been any number though, when you take the derivative of that constant function, you get 0. Now we're going to talk about the power rule, and the power rule is going to change your life. This says if n is a rational number, then the function f of x is equal to x to the nth power is differentiable, and d dx, the derivative of x to the nth power, is equal to n times x to the n minus 1 power. For f to be differentiable at x is equal to 0 though, n must be a number such that x to the n minus 1 power is defined on an interval containing 0. So let me explain this to you real quick and show you how this is going to change your life. Instead of doing the whole limit process, the power rule says you can actually take a function x to some power, and if you want to take the derivative of it, you just take the exponent, move it out front. So it's going to be n out front times x, and now your exponent, just subtract 1 from. So it's going to be n times x to the n minus 1 power. So how does that look in practice? We have a function right here, y is equal to x squared. If we want to take the derivative of it, dy dx, all we would have to do according to the power rule is take this 2, move it to the front, so it'd be 2 times x to the, and then your exponent, subtract 1 from. So this would be 2 minus 1, which would be the first power. So your derivative of y is equal to x squared should be 2x to the first power. So let's check this out. If I were to do this with the limit process, I have the formal definition of the derivative. Again, f of x plus delta x means I take x plus delta x and plug it in the function for x. So this right here, f of x plus delta x, is going to turn to x plus delta x squared. F of x is just equal to our function x squared, and then delta x stays delta x. Now, x plus delta x, the quantity squared, I need to FOIL. So that's the same as x plus delta x times x plus delta x. So when I FOIL that, it looks something like this. I combine like terms, so x squared cancels out with this negative x squared over here. And then in the numerator, I can factor out a delta x, which cancels out with the delta x in the denominator. I can then evaluate this limit by plugging in 0 for delta x, and I get 2x, which is exactly what we thought it would be using the power rule. So from now on, we can use the power rule instead of this long and drawn out limit process, and it's going to make your life a lot easier. Next, we're going to talk about the constant multiple rule. This says if f is a differentiable function and c is a real number, then c times f is also differentiable, and d dx, the derivative of c times f of x, is equal to c times f prime of x. So all this is saying is that if you have a function and that function is multiplied by a number, instead of taking the derivative of that number times the function, you can take the derivative of that function and then just multiply that number on at the end. So how does that look in practice? We have y is equal to 3x squared. So what the constant multiple rule says, if you have a function x squared and a number multiplied to the front, this 3, so 3 in this case would be our c value, f of x would be our x squared. If I wanted to take the derivative of this, all I would have to use is the power rule for our x squared, and I would get 2 times x to the first power, and then multiply that by this 3, and I should get 6x to the first power. So let's see how this works. If I do it with the limit process to prove that it works, I'll take this x plus delta x, plug it in our function for x, and that'll give me f of x plus delta x. So that'll turn into 3 times x plus delta x squared. F of x is just our function, 3x squared, and then delta x goes in the denominator. So here, again, I need to FOIL this guy right here, and then I can distribute the 3. Once I do that, I can combine like terms. The 3x squared and the negative 3x squared are going to cancel out. I can factor out a delta x from the numerator, cancel it out with the 1 in the denominator, so these two cancel out, and I'm left with 6x plus 3 times delta x. Now I'm taking the limit as delta x approaches 0, so I evaluate this by plugging in 0 for delta x, and I end up just getting 6x. Exactly what we thought using the power rule and constant multiple rule this derivative would be. Next, we're going to talk about the sum and difference rule. This says the sum or difference of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of f plus g, or f minus g, is the sum or difference of the derivatives of f and g. So here, all this is saying, it's kind of cool. If you have two functions that are differentiable, and you were to add them together or subtract them, and you want the derivative of that new function that you've created, all you have to do is take the derivative of each of those functions and either add them together or subtract them, whatever you were doing. So here, the derivative of f of x plus g of x is equal to f prime of x, the derivative of f of x, plus g prime of x, the derivative of g of x. Same thing with subtraction. So let's see how this works. If I have a function, 2x plus 1, and we'll pretend for a second these are two separate functions. 2x is a function and 1 is a function. So 2x would be my f of x, 1 would be my g of x. Now, if I want to find the derivative of this, all I have to do is take the derivative of each of those terms and add them together. So the derivative of 2x, if I use the constant multiple rule and the power rule, so the derivative of x would just be 1 times x to the 0 power. Remember, since I have my constant out front, I have to multiply that to the derivative of x. So 2 times 1 is going to give me 2. The derivative of 1, since that's just a constant, is going to be 0. So my derivative here should be 2 plus 0, which is 2. Let's see if that works out. With the limit process, we have the limit as delta x approaches 0, and here's our formal definition. We're going to take x plus delta x, plug it in the function for x. Then over here, f of x is just going to be f of x, 2x plus 1. We then simplify this. We're going to distribute the 2. We distribute this negative sign over here, and we combine like terms now. Negative 2x and 2x cancel each other out. 1 and negative 1 cancel each other out, and we're left with 2 delta x over delta x. Those then cancel out, and I'm left with the limit as delta x approaches 0 of 2, which is just 2. And that's exactly what we thought it would be. Derivative of 2x, we said was 2. The derivative of 1 was 0. 2 plus 0 gave us 2. You want to know my favorite outdoor sport? Fly fishing! Example time. Okay, example 1 says use the rules of differentiation to find the derivative of the function. So here's how this works. I have f of x is equal to negative 2. This is clearly a constant function because we have f of x is equal to a number. So anytime you take the derivative of a number, by the constant rule, we said that's equal to 0. And you're done. Here we have y is equal to 8x cubed. So there's a couple things that need to happen when I take the derivative here. First, the constant multiple rule says I have a number multiplied to my function, x cubed. So I'm actually going to take this 8 and I'm going to move it out front, and I'm just going to take the derivative of x cubed. So x to the third power, based on the power rule, is going to be 3x to the 3 minus 1 power, so 3x squared. Then I am going to multiply that 8 to the derivative of x cubed and get my final answer, my final derivative, which is 24x squared. For c, I have p of s is equal to 1 over s squared. Now for this, you might be like, what do I do? We didn't learn anything about this. Well, s squared, you know, if I were to move this to the other side of the fraction bar, it would turn into s to the negative second power. And now we can just use the power rule. When I take the derivative of p of s, I'm going to do exactly what the power rule says. I'm going to take this negative 2, move it to the front of s, so it's going to be negative 2s to the negative 2 minus 1 power. So what is negative 2 minus 1? That's going to be negative 3. Now, if I want to rewrite this, I take this s to the negative third power, move it back to the denominator, and I have my derivative. Part D, I have h of k is equal to the cube root of k. Now here's a question, what do I do with a radical? I need to write this so that it has an exponent. I'm going to change my radical so that it's written in a rational exponent format. So instead of the cube root of k, I'm going to write k to the 1/3 power. These are the same. I could then use the power rule, just like we were doing before. When I take the derivative of k to the 1/3 power, I'm going to move this 1/3 out front, so it's going to be 1/3 k to the 1/3 minus 1 power. Now 1/3 minus 1 is going to be negative 2/3, because 1/3 minus 1 is the same as 1/3 minus 3/3. So you get the negative 2/3 power. And if I want to rewrite this with a positive exponent, I can move it to the denominator, and it's going to be 1 over 3k to the 2/3 power. Okay, so here we have f of x is equal to pi. Now this is a constant function because pi is just a number. So if I want the derivative of a constant function, we know that that is just going to be 0. Anytime you take the derivative of a constant, it's going to be equal to 0. Over here, this looks tricky for s over 5, but if you realize that our function is just s and 4/5 is a number that's multiplied to the front, we can use the constant multiple rule. Just take the derivative of s and then multiply that answer by 4/5. So what is the derivative of s? If I take the derivative of s, this is s to the first power. I bring the 1 out front, and it's going to be 1 times s to the 1 minus 1, which is 0. So 1 times s to the 0 power, anything to the 0 power is 1. So 1 times 1, we get 1. And that's how that works. Anytime you're taking the derivative of s or x or some variable to the first power, it's just going to be equal to 1. And we saw that earlier when we took the derivative of 2x. That was just equal to 2 because the x turns into 1. Here, 1 times 4/5 then gives you the derivative of our p of s, which is 4/5. Here, this looks tricky, but all you have to do is write it so that s has a negative exponent, and then we can use the power rule. Here we also have a 5 multiplied out front. We're going to wait until the end to do that by the constant multiple rule. So if I take the derivative of s to the negative 3rd power, I take that negative 3, move it out front by the power rule. So it's going to be negative 3s to the negative 3 minus 1 power. Negative 3 minus 1 is going to be negative 4. So I can then multiply that by 5, finishing the constant multiple rule, and I get my derivative, p prime of s. And you can see we moved s to the negative 4th back to the denominator to give it a positive exponent. Here, anytime you have radical, again, and you want to take the derivative, you need to write it so that it's a rational exponent. The square root of x is the same as x to the 1/2 power. Now what I can do is take the derivative of this using the constant multiple rule. I don't have to multiply the 2 on until the very end. I'm just going to take the derivative of x to the 1/2 power. Using the power rule, anytime I take the derivative of x to the 1/2 power, I'm going to move that 1/2 out front. So it's going to be 1/2 x to the 1/2 minus 1 power, or 1/2 minus 2/2, which is going to be negative 1/2. So I have 1/2 x to the negative 1/2 power, and then the 2, remember, stays out front by the constant multiple rule. I then multiply the 2 times the 1/2. Those cancel each other out, and I'm left with x to the negative 1/2 power, which I then move to the denominator of my fraction to make it a positive exponent. Now, example 2, we're doing the same thing except we're dealing with longer functions this time. So here we want to take the derivative of x squared minus 4x plus 5. So if we want to take the derivative of this function, find f prime of x, what you're going to do, you're going to use the sum and difference rules. If you have a function with multiple terms, you're going to treat them as separate functions, and you're going to take the derivative of each of those terms. And that will give you the derivative of your whole function. So here, if I want the derivative of x squared, using the power rule, that's going to be 2x to the 1st power. If I want the derivative of 4x using the constant multiple rule, I'm just going to take the derivative of x, which is 1, and then multiply it to 4. Over here, derivative of 5, that's a constant, so that's going to be 0. So here I have 2x minus 4 times 1 plus 0. That simplifies to 2x minus 4, which is my derivative. Here, I'm going to do the same thing. I want to take the derivative of this particular function, and anytime you have a function with multiple terms, I'm going to treat each of the terms as separate functions and take the derivative of each of those terms. So here, I'm going to rewrite this instead of negative x to the 4th over 2. I'm going to rewrite it so that you can see that this is a number that is multiplied to the front of this function. That way you can use the constant multiple rule. So if I were to take the derivative of this, I'm going to take the derivative of each term. For this term right here, this negative 1/2, I'm going to leave till the end and multiply it on after I take the derivative of x to the 4th. What's the derivative of x to the 4th? By the power rule, that's going to be 4x to the 3rd power. Over here, again, I am using the constant multiple rule because I have a 3 out front. So I'm going to take the derivative of x cubed, which is going to be 3x squared, and then multiply that by 3. Here, the derivative of 2x, again, constant multiple rule, I have this 2, so I'm going to take the derivative of x, which we know is just 1, and then multiply it to the 2. Now that I've done that, I can finish my constant multiple rules by multiplying the numbers that were on the outside to the derivatives of our functions, and I can simplify and get my derivative of this particular function. The itsy bitsy spider went up the water, you try! Okay, so here, what I want to do is I want to take the derivative of f of t. And to do that, I need to take the derivative of each of its terms. So here, derivative of 4t. Using the constant multiple rule, I'm going to multiply whatever the derivative of t is by 4. So what's the derivative of t? That's going to be 1. Anytime you take the derivative of t or x or s, right, it's just going to be 1. Then you're going to multiply it by 4 by the constant multiple rule. Here, again, constant multiple rule, I have 3. So I'm going to take the derivative of t to the third power. That's going to be 3t squared. And then multiply it by 3. So if I were to simplify this, I end up getting f prime of t, which is my derivative for minus 9t squared. For part B, I'm doing the same thing. Here I have x cubed over 5, which I'm going to rewrite as 1/5 times x cubed. That makes it a little easier when you're using the constant multiple rule. Now, I'm going to take the derivative of this particular function, meaning by the sum and difference rule, I'm going to take the derivative of each of these terms now. Here, this requires the constant multiple rule because I have 1/5. So I'm going to take the derivative of x cubed using the power rule. And that's going to be 3x squared and then multiply it by 1/5. I am using the constant multiple rule because I have this 5. So I'm going to take the derivative of x squared using the power rule. So that's going to be 2x to the first power and then multiply it by 5. Here, the derivative of 9 we know is just 0 because derivative of a constant is going to be 0. I can then simplify this by multiplying our constants that were out front and I get our derivative of the given function up here. Example 3, we are again taking the derivative just of more complicated functions. This seems super complicated, but all I have to do is instead of writing this 4x cubed minus 2x plus 5 all over x, I can actually take this x and put it under each of the terms. I can then simplify this function so that it's just x cubed over x. That cancels out and just leaves me with 4x to the second power. 2 to the x over x, these x's cancel out. I'm just left with minus 2. And this is going to be plus 5 over x to the first. Remember, I don't want to take the derivative of a fraction right now. So what I'm going to do is rewrite this x to the negative first power. Now, if I take the derivative here, the derivative of this particular function means I'd take the derivative of each of these terms. Derivative of 4x squared. Remember, constant multiple rule, I have 4, so I'm going to leave that to the end and just take the derivative of x squared, which is going to be 2x to the first power, then multiply that by 4. Derivative of 2, that's a constant, so that's going to be 0. Derivative of 5x to the negative first power, constant multiple rule, I'm going to leave the 5 out to the end and just take the derivative of x to the negative first power using the power rule. So that's going to be negative 1 times x to the negative 1 minus 1, which is negative 2 power, or negative second power. Now if I simplify this, 4 times 2x gives me 8x, 5 times negative 1 is negative 5, and then the x to the negative second comes to the denominator, and I have found the derivative of h of x. Here, it's the same thing. I take this t, put it under each of the terms, and then I can simplify this further. This 3t squared over t, one of the t's cancel out, and I'm just left with 3t. T over t turns to 1, and instead of writing this as 1 over t, I'm going to write it as t to the negative first power. Now all of these terms are easy to take the derivative of using the sum and difference rule. I can take the derivative of each of these terms. So in this first one, derivative of 3t, I want to use the constant multiple rule first, bring the 3 out, and just take the derivative of t, which is 1. So it's going to be 3 times 1. Here, the derivative of 1 is going to turn to 0 because derivative of a constant is just 0. And then over here, the power rule, when I take the derivative of this, negative 1 is going to come out front. So it's going to be negative 1 times t to the negative second power. Now, if I simplify all of this, I'm going to get 3 minus 1 over t squared. Be careful not to subtract 3 and the negative 1 because these are multiplied together. Now, example 4 says find the slope of the graph of the function at the given point. Use the derivative feature of the graphing utility to confirm your results. So I'm given a function and a point, and I want the slope of the graph of this function at this point. Now, slope of the graph of a function at a given point, that is the instantaneous rate of change. That is the derivative of the function at that particular point. That is the slope of the tangent line. All of those things mean the same thing. In order to find the slope of the graph of the function at this given point, I want the slope of the tangent line to the graph at this given point. Meaning, I want to find the derivative here of this function and plug in the point of tangency. That's all you have to do. So I take the derivative of this function, and in order to do that, I'm going to rewrite this 4 over t as 4 times t to the negative first power, because that'll allow us to use the power rule. I then use the sum and difference rule to take the derivative of each term. The derivative of 2 we know is just 0 because the derivative of a constant is 0. The derivative over here is a little more complicated because I have this 4 out front, so I'm going to leave it out front by the constant multiple rule and just take the derivative of t to the negative first using the power rule. So that's going to be negative 1 times t to the negative 1 minus 1, which is negative second power. Now, if I were to simplify this and bring the t to the negative second to the denominator, I have my derivative. Now, this is not your answer. This is the derivative of this function. But I want the slope of the graph of the function at this given point, 4, 1. I want the slope of the tangent line. So in order to do that, the slope of the graph of that function at this given point, I'm going to take this point and plug it into the derivative. So there's only an x here, or in this case a t. So I'm going to plug in 4 for t in order to find the slope of the graph at that particular point. So I plug in 4. Simplify, and I end up getting g prime of 4 is equal to 1/4. That means that the slope of the line tangent to our particular function, g of t, at 4, 1 is 1/4. Or the slope of the graph of our function, g of t, at 4, 1 is equal to 1/4. To confirm this with the graphing calculator, here's how you do this. You press the math button. It brings up this menu. You're going to go down to 8. It says n derivative. You're taking the derivative, and it's going to look something like this. Even though this says t, you're just going to put in x because that's the only variable that your calculator allows right now. So you're going to put in x here, and then in this spot, you're going to put your function, 2 minus 4 over x in this case. Now, in this last part, put what you're going to plug in, which is 4, because that's the x value or t value in this case. And you end up getting your derivative, which is 0.25 or 1/4. And your answer checks out. You guys remember Charlotte's Web? Great book. You try. Okay, here we're doing the same thing. We're finding the slope of the graph of the function, this function, f of x, at this particular point, 2, 8. We're finding the instantaneous rate of change. We're finding the slope of the tangent line to the function at this given point. All those mean the same thing. So here, first thing I'm going to do is I'm going to FOIL this guy out. X minus 4, the quantity squared, FOILs out to x squared minus 8x plus 16. I can then have this 2 distributed to each of the terms. Now, when I take the derivative of this function, I'm going to take the derivative of each term by the sum and difference rule. When I do that, for this particular term, I'm going to use the constant multiple rule because this 2 is out front. So I'm going to leave that out and just take the derivative of x squared using the power rule. So I'm going to get 2x to the first power and then multiply it to that 2 that was already out front. Here, I'm doing the same thing. Constant multiple rule, I take the derivative of x and then multiply it to 16. So derivative of x is just 1, and then I multiply it to that 16. Here, the derivative of 32, that's a constant, turns to 0. Simplify, and I end up getting the derivative of my function. But this is not what I'm trying to find. I'm trying to find the slope of the function at this given point, or the slope of the tangent line. To do that, I take my derivative and plug in the point of tangency. So I take my derivative, and now I'm going to plug in my point of tangency, 2, 8. Well, the only thing this has is an x, so I'm going to take this 2 and plug it in for x. When I simplify, I end up getting 8 minus 16, which is negative 8. That means that the slope of the line tangent to f of x at 2, 8 is negative 8. The slope of the line that is tangent to the curve, or the slope of the graph at that particular point of this function, is equal to negative 8. Check our answer with the graphing calculator. Press the math button, go to 8, press enter. Now I have to enter my function, which is 2 times the quantity x minus 4 squared. I put that here, and I'm taking the derivative with respect to x, so I put an x here, and then I put the number that I'm plugging in for x here, which is 2. Do that, you get negative 8, your answer checks out, and you're done.